Hiya! Welcome to the last video for this week, where we give an example of reflections or this Q operator, and then we're going to finish things off this week with a proposition that kind of classifies all orthogonal linear operators in two dimensions. So let's start off right away with the example. So before we do the example, so let's remind ourselves what this Q operator is. So this Q operator we basically said is, okay, what happens when I take my K, right? So this K, I set to odd. And then I notice that if K is odd, I get this matrix, cosine phi, sine phi minus cosine phi. And this is really just a multiplication of my P matrix, my rotation matrix, with some reflection where I swap E2 and E1. I flip E2 over its hyperplane, sorry. So I have Q is just a rotation times a reflection. So let's look at an example of this. Here I start off with some orthonormal basis, E1, E2 in two dimensions, and I'm going to take the same vector as before, so 2 times E1 plus E2. And this time I'm going to let phi be equal to 0. So what happens when phi is equal to 0? Like this should maybe not do anything, but actually it should actually do something. So let's actually see this. So Q naught should theoretically just be R, right? Because if I'm not, so remember my P phi, right? This is the rotation over phi. And here I'm saying phi is equal to 0, so no rotation. So in other words, intuitively, I should expect Q naught to be R. So intuitively, Q naught should be R. So let's actually see if this turns out to be the case. Is it not the case? And kind of go from there. So let's actually just plug things in. So Q naught of X, this is, let's look at the formula we had from before. This is x1 cosine of phi plus x2 sine of phi. So we have 2 cosine of 0 plus sine of 0 of E1. So this was my x1, this is my phi, this is my x2, which is 1 times my phi, plus, what do I have on this side? We have sine of 0 minus this time cosine of 0 of E2. So just as before, we have x1 phi, x2 phi. So what are these numbers? What's cosine of 0, sine of 0, etc.? Cosine of 0 is just 1, sine of 0 is 0, sine of 0 is 0, and cosine of 0 is 1. So we can plug these in. So we get 2e1 plus, minus. I think it should be minus, right? Plus minus 1, yeah. So minus e2. And that's it. So that's Q of 0. And in reality, if you think of what happened, well, all I did, I kept the E1 where it was, the E1 stays, and the E2 flipped sign. So it's exactly what we expected, right? It just flipped E2 to its minus. So it's exactly what we wanted. So let's look at something a little more complicated. Let's look at Q of pi over 2 of the same thing. So in other words, this is going to be the same, except I'm changing all the zeros for pi over 2 instead. I have 2 cosine of pi over 2 plus sine of pi over 2, E1 plus 2 sine pi over 2 minus cosine of pi over 2 of E2. So let's remember cosine of pi over 2 is 0. This is 1, this is 1, and this is 0. And so what I have is E1 plus 2E2. Okay, so let's kind of look at this. So there's kind of two ways to look at this linear operator, right? So we have Q0 basically just swapped E2, but somehow when I do Q of pi over 2, I'm not just swapping it, I'm like moving it over in some sense. So in other words, there are two kind of geometric intuitions to kind of look at this. Two geometric intuitions. Of Q. So one It's the reflection of the line spanned by E1 followed by a rotation B. So in this case, in our previous example, it's pi over 2. I guess here we'll do a geometric interpretation of Q pi over 2. We'll do that. Of rotation pi over 2. And the second intuition is it's actually just the reflection in the line spanned by E1 plus E2. So this might be a little harder to see. So we'll actually see this in figure 2. So let's kind of look at this. So here we'll zoom in again. So here is so we'll only look at one basis this time. We won't look at the other one. So here, if I start off with this one, I have E1 plus E1 plus E2. So this is the same X that we saw in a couple examples before. So if I look at Q0, right, this is just R. This is what we had said. Remember that this is just flopping my E2. So in other words, I have my E1 and then I do minus E2. And so this gives me Q naught of X. Well, what is my Q pi over 2? Well, pi over 2, remember, this gave us the formula E1 plus 2E2, right? 1 plus 2E2. So this is 2E2 plus E1, which gives us here. So this is my Q of pi over 2. But remember what we said is we can actually look at it in two different ways. We can either look at it as going to R. So we first go to R. And then we rotate, sorry. So this is reflect over E2. So reflect over this line. We'll do it this way. So here is my reflection line here. So here we reflect it over. So that's why it brought this vector down. So we can kind of do it here. And my reflection is there. So this basically took this vector and brought it down. That was the reflection. So that is R. And then afterward, we would do a rotation by pi over 2. Now, since we have E1, E2, this means the rotation is going to be anti-clockwise. So this is why this rotation of pi over 2 took me up in this way. Now, the second way to kind of look at this, right? So this is way 1. So this is way 1. This might be confusing. So actually, we'll do this. This is number 1. This direction is number 2. This is the second way of looking at this. And this is really looking over. So here we've actually drawn my X plus 1 line, my E1 plus E2 line. And here I have the original X. So here I have my original X. And this is really just a reflection over E1 plus E2. So these are the kind of two ways to think of this. So this Q operator can be thought of as some reflection. This angle doesn't, it's a little harder to see where this angle plays in, which is why you might want to consider it as R and then a rotation. But for now, this is kind of, we'll leave it at here, and we'll kind of see this later on. So we'll end this week on this final proposition. In that, if I started off with some arbitrary orthogonal linear operator, we already saw two things, that if m is even or odd, then the determinant is either 1 or minus 1. So we know that the determinant in particular will always be plus or minus 1. If it's positive, then this is going to give us that k is even, right? So if it's an even one, then we're actually having a rotation. So this rotates a vector by phi. And if it's negative, then remember this gives us the Q operator, Q of phi. And this is just a rotation rotation, and a reflection. So we reflect first, and then we rotate. So this is first, and this is second. And that's it. So we will end this week here. Next week, we'll actually look at what happens when we look at 3 dimensions and kind of start classifying things there. And that's where Euler's theorem kind of will fit in. So we'll stop here, and I will see you next week for week 4. Peace.